Hi, I'm Rohan Bull, and this is my analysis of Lab 2, Lines of Charge. So the overview of this is to take our data from Lab 1 and basically make it more realistic. In Lab 1, we took two negatively charged pieces of tape, held them up to each other, and measured the distance that they were repelled. And then for the online portion, we modeled the tapes as a single point charge, which we calculated to be negative 1.2 times 10 to the negative 8th coulombs. For Lab 2, we do the same basic procedures, but for the online portion, we instead model it as a line of charges which, with a calculated charge of negative 5.98 times 10 to the negative 8th coulombs. So some of the applied concepts are Coulomb's law, F equals kq1 q2 over r squared, which relates relates electric fields and forces of two charges that are far apart from each other, and the superposition of infinitesimal charges, which is just the integration across the area of an object. So here are the procedures from Lab 1, where we create two negatively charged pieces of tape by sticking two pieces of tape together and quickly ripping them apart. We should have as little contact with our skin as possible, and in order to confirm that they are in fact negatively charged, you take a plastic pen, rub it on the piece of tape, and if it repels, then it is negatively charged. We hold up one tape underneath the other, and then measure the vertical distance the other tape is repelled. So here are some assumptions I made for this lab. I assume that both tapes have the same charge, which they wouldn't normally. No air resistance. I assume that the charge is spread out evenly throughout the tape, and that I assume the tape's mass by using its length to calculate it. So here's some of the data I gathered. The data used from Lab 1 was the tape length, 0.216 meters, tape width 0.0225, vertical distance 0.025, and approximated charge negative 1.2 times 10 to the negative 8th coulombs. And for Lab 2, we take all of these numbers, we use the charge from Lab 1 and repeat this charge over an infinitely small portion of the tape and repeat it multiple times to find a new net electric force. We use this new net electric force to calculate the magnitude of the new E-net on the top tape with gravity, and then adjust all the total values accordingly. So here's some of the coding, like for E field, I found the R vector with observation location minus charge particle position, R magnitude, the square root of the X, Y, and Z variables squared, R hat, R vector over magnitude, and the new E, which is 1 over 4 pi epsilon 0 times the charged particle Q over the magnitude of the position times the unit vector r hat. And then the bottom part is the line. It creates the line of charge. Most of this was already given in the starter code. So with the graphics, a lot of this was also already given in the starter code. However, this is just mainly to calculate all of the small green and red arrows that show the forces of gravity and the forces of repulsion of the tapes. So for the reflection questions, what if you had modeled each of your tapes as a single point charge like in the previous lab? Well, doing this would just give us the result of lab 1 because it was exactly what lab 1 was, to model the tapes as a single point charge. So what we got from it was negative 1.2 times 10 to the negative 8th coulombs versus the distributed negative 5.98 times 10 to the negative 8th coulombs from this lab. As you can see, they are quite different values from each other. Well, why do these estimates differ? Which value is more likely to be close to the real value? And why? Well, these estimates differ because the more you simplify an object, the more inaccurate the results become. If we were to simplify an entire piece of tape as one point charge and give it only one force, it would be quite inaccurate versus spreading out the charges into multiple pieces and then calculating each of those. So the more accurate result would be the pieces of tape set as a line of charges.